Hey, math friends. So our learning target today, we're starting unit 7, is that I can calculate or find experimental probabilities. Now you've done probability in elementary school, so this lesson should go A-OK. You've done most of this before. You will want a calculator in our work because a lot of that you can just enter quick into your calculator. You can also do it by hand if you prefer. So probability is the experimental probability is based on the based on repeated trials of an experiment. So flipping coins is probably one of the most well-known experimental probabilities of something that you can do in class that's inexpensive for a group of kids to kind of see how a repeated trial works. So flipping a coin over the course of time. We always say 50-50. What we mean by that is we assume that it should be 50% heads, 50% tails. The more you do the experiment, the more likely you'll get to what we call theoretical probability, which is the next lesson. Today is just basically on the experiment. So when you flip the coin 50 times, how many heads did you get? Is it guaranteed that you're going to get 25 heads and 25 tails? No. So today's work is just basically, what did you get? What were your results? So almost a little bit easier than predicting what we think should happen, which is tomorrow's lesson. So the formula for probability, this capital P here that I just typed up on the screen that you just saw come up in pink is the probability of something happening, the probability of an event. Event meaning getting a heads when you flip a coin or getting a 6 when you roll the dice, whatever the event is. But that capital P means probability. Super easy formula here. It's just the number of times that the event occurs divided by the number of trials. Now you can always use cross products and proportions, but in today's work I'm actually going to convert out of that process and talk about just dividing and multiplying by 100 to get the percent. So, for example 1, if you had 13 out of 20 emails in your inbox that are junk mails, we would say, what is the probability of junk email based on the experiment, based on the data that happened? So probability of junk then. So we would say, well, 13 out of the 20, there's your of there, out of the 20 is junk email based on the experiment. You just opened your email, and you counted 13 out of the 20 junk. Okay, so what percent of that? Now what we've been doing in the past is doing proportions cross product because that's the Minnesota learning target in this course, pre-algebra. But a faster way to do that is I'm going to introduce that to you now. Some of you maybe have been following that trick all along. This is just a division sign. We've covered that before. We're just going to divide down. So when we type 13 divided by 20 in our calculator here, I get 0.65. You don't have to write all of those steps out in the process once you see it once. To get it to a percent, we need to move the decimal 2 places to the right, which we just covered in a previous example of rate, the simple interest lesson. We talked about that conversion, which means it's 65%. Percent is out of 100, so we'd have to multiply that by 100 to get to the percent. So 65% junk mail, which is probably true in our email inbox as well as our actual physical mailbox. So then what is the probability that it is not junk? So we would say that the probability that it's not junk is 35% because these are what we call complementary events, meaning the percent that's junk plus the percent that's not junk should equal all 100% of all of the mail that comes in. So there's our first example on experimental probability. It's just a fraction converted to a percentage. So pretty easy peasy once you get the hang of it. So let's take a look at another example. So this one. It rains 2 out of the last 12 days in March. Excuse me. So the rain. It rains 2 out of the last 12 days in March. What is the experimental probability? So that's what we saw happen. We're going to use that to make a prediction. What is the experimental probability that it rains, how many days it rains in March? Now March, that question isn't written very well. Sorry about the poorly written question there. What I'm asking you is what would we predict? So this lesson is about the experimental probability and how to predict something based on that. So March has 31 days. How many days do we predict it should rain based on the experiment? So the experiment being in 12 days we kept track. It rained twice. What do we predict should happen out of 31? This now is that proportional idea because it's not a percent. So 12x is equal to 62. Divide by 12. Divide by 12. Where am I getting that 62? It's that 31 times 2. We're trying to predict how many days do we anticipate rain over the course of March, which is 31 days long. So we're predicting about 5 days of rain. I'm getting 5.1 days, but I'm just going to say we predict probably about 5 days of rain. All right. Let's take a look at another example. At a clothing company, an inspector finds 5 defective pairs of jeans in a shipment of 200. Okay. So what percent are defective? So what's the probability that we got defective jeans? Now that happens, right? They come back, the zipper doesn't work correctly. There maybe is a hole in it when there isn't supposed to be. Sometimes we do want to buy jeans that do have holes in it, so that's confusing. But those jeans end up in a store like a TJ Maxx or things like that because there might be some little tiny defect and it didn't pass inspection. So we would say that 5 out of the 200 pairs of jeans are defective. So let's figure out what percent of the jeans is that. So what we're going to do is we're simply going to just divide down. Now you could do that cross products x over 100 like we did in the last 2 units, but I'm going to avoid that as much as possible today just to show you another way of looking at that. So I'm going to divide down 5 divided by 200. And when I do that, I get 0.025. When we convert that to a percent then, that becomes 2.5% of the jeans are defective. So pretty good rate for them really because nearly 97.5% of the jeans are fine and they end up in the store sold at full price. So that's the amount of jeans that end up in like a TJ Maxx or a store where they're selling it at a discounted price because there's some defect in it. Okay, so let's use prediction now. Use that to make a prediction. Now, there are multiple ways to approach this next question. I'll try to approach it in the easiest way. About how many would you expect to be effective in the shipment of 500 pairs of jeans? Probably the easiest approach is just using that we know 5 out of 200 are defective in our experiment. So how many would we predict defective out of 5,000? Just a prediction. No guarantee that it's correct. That's option 1. Or option 2, you could have worked off of this percentage. But I think this might be a little bit easier based on the unit we just came off a proportion cross product. Multiplying cross products here then, we end up with 200x is equal to 25,000. I'm out of room there on the right hand side, so I'm going to squeeze it in down here. Divide by 200, copy, paste, copy, paste. So we're looking for what do we anticipate as a company, or what are we okay with in terms of defective jeans? Probably, most would say, well, they don't want any defective jeans. True, but never do we get 100% perfection. So 125 jeans we anticipate to be defective out of the 5,000. That's a 100, not a decimal point there. That should be just a 100. Okay, so there's how we make predictions. Let's take a look at a couple other examples. I'm going to skip around here until I find what I think I want. Yeah, these are all really good ones. I'm going to skip that one. I'm going to skip that one. Eggs. You check 20 cartons of eggs. 3 of the cartons have at least 1 cracked egg. What is the experimental probability that a carton of eggs has at least 1 cracked egg? My recommendation to you is that I'm just going to have you go try it and see what happens, and then I'll talk about my recommendation to you. You should be doing it. You should be pausing the video and trying this. Come on. It's your journey. All right, coming back now. You check 20 cartons of eggs. So I always do that when I'm buying my eggs. I open the eggs and see if any are cracked. Of course, I don't want to purchase them then. 3 of the cartons have at least one cracked egg. What's the probability that you have at least one cracked egg? So the probability of a cracked egg, not easy to write here, so bear with my writing, is that we have 3 out of the 20 that we checked. So let's talk about percent. What percent? What's probability and percent mean the same thing. So 3 divided by 20 is equal to 0.15. Converting that to a percentage then, because I just divided down here, that's how I got that, I get 15% of the cartons have at least one cracked egg. Notice the word probability is exactly the same as percent. They mean the same thing, just different forms. So probability is sometimes given as a fraction, sometimes given as a decimal, and sometimes given as percent. All of these forms are the same value. So we found out that the experimental probability when we open 20 cartons, that we end up with 3 out of the 20, which is equal to 15% of the cartons have at least one cracked egg. Awesome. Next problem. Let's take a look. This is going to be a prediction question. There are 105 lettered tiles in a board game, so like Scrabble or something. 105 total. You chose the tiles shown. So you reach in. Your experiment is that you reach in and you grab these tiles that are listed to the right here out. Now I have the crayon. Not really sure why I want the crayon, but that's okay. Looks like we have 1, 2, 3, 4, 5, 6, 7. Looking like 7 tiles. Okay. What is the probability that we expect them to be vowels in the entire group of 105? So first what we have to start with is our actual experiment. So if I look at the vowels that I drew out in my random experiment, that's a vowel, that's a vowel, that's a vowel. Reminder, A, E, I, O, U, and sometimes Y are vowels. So based on my experiment of getting vowels, I got 3 vowels out of 7 when I just did a sample. I grab 7. How many do I get? That's my experiment. Now we could convert that to a percentage and find the percentage and all that. But the question's asking us to make a prediction of if the board game has 105, using our sample, what do we predict? And this is a situation where I'm going to use my cross products that I know so well. So 105 multiply across. So we get 7x is equal to 315. Cool. Isolate, divide by 7. And we're looking for how many vowels would we predict out of 105. So you should be doing it. Do it, do it, do it, do it. My prediction then is that we would end up with 45 vowels out of the entire board game of 105. So that's using the experiment of drawing 7 to make a prediction out of the entire game board. It's called really sample size. All right, I'm going to skip around and let's see what we have. That's another prediction question. I'm not going to do that one. I'm not going to do that one. All right, I think this might be our last question today. Why don't you pause the video and give this one a shot? This is also a prediction question. Cool. All right, guys, you should have tried it. Let's see how you did. You have a package of 20 sorted cards. You reach in and pick 4. Okay. How many of the 20 cards would you expect to have flowers on them? So let's look at our experiment. Our experiment is 4. And we're talking about cards that have flowers. What's the probability of cards that have flowers? In our experiment, I think we only have 1. I'm having a hard time seeing. My eyes aren't working so well, but it looks like 1 out of the 4 in our experiment says flower. So if the entire package has 20 instead of 4, like we had in our experiment, how many do we predict to have cards or have flowers on the card? Now I see a nice little pattern there of times 5 times 5. So I'm not going to go through all those steps, but I can see that 5 cards, we predict 5 cards will have flowers out of 20, using our experiment to make a prediction of what we think should happen. And so our probabilities today, probability is that capital P of the event. So the last one is the probability that we get a flower on a card. That's the event is written as a fraction. Now, there are times where we just simply can divide that down and get the decimal and then get the percent, right? Just what percent of the time did that happen? There are other times, though, where we're setting up a proportion and using that we got 1 out of 4 cards that had flowers on it in our experiment. So what do we predict would happen out of the entire package of 20? So sometimes we're doing predictions, cross products, and sometimes we're just trying to get the percent. Okay, so there's a lot going on there, but very familiar language from elementary school. That's it for today, and I can find experimental probabilities. Have a glorious night. Woo!